Thank you guys for coming in so calmly and quietly and for chilling out. Welcome. Please let me know if you need me to talk any louder or anything. I can yell, I can shout, but we're a pretty tight group here. So feel free to move closer as well. I'm just going to start us off with a brief introduction, and then we'll go ahead and get right into the panel and start asking our experts here some of our questions. Welcome to the Bethesda Green Innovation Lab's Summer Speaker Series, tackling environmental challenges through sustainable entrepreneurship. During this series, we're discussing ideas that impact people, the planet, and profits. My name is Emily Bernard. I'm the program manager of the Innovation Lab here at Bethesda Green, and we appreciate you joining us for the last session of the 2023 Summer Speaker Series, where today specifically we'll discuss using AI for climate solutions. I'd like to take a minute just to introduce you to our work here at Bethesda Green, which we organize under two primary categories, Be Green Business and Be Green Living. The Be Green Living program elevates community engagement and enhances the quality of life for local residents through projects like our efforts to improve stormwater management, promote street-level recycling, and improve access to green space. Under our Be Green Business program, we support leaders who are building for-profit models around innovative and sustainable solutions to tackle environmental and social challenges. We welcome mission-aligned idea stage through seed stage startup companies to our innovation lab. I invite anyone who is ready to join our exciting and growing community to grab some food and drink and chat with me afterwards. And finally, before we jump into today's panel, I'd like to acknowledge our amazing network of partners and sponsors who support us and support the work that we do, and thank you so much for everybody who is a part of that. So today, emerging artificial intelligence and machine learning technologies are already changing the way we all work and interact, but they could also play a role in our evolving fight against climate change. As we'll discuss today, AI works by processing vast amounts of data and finding patterns in that data in order to learn and make decisions the way people do. This can be used to map, model, and predict changes in various natural ecosystems, from the ice caps to coastlines and everything in between. Like all innovations, there will be challenges and considerations for our growing use of AI in the pursuit of sustainability. So, to share their experience with us today, we're welcoming Kumar Mainali, the lead data scientist for the Chesapeake Conservancy, a nonprofit organization with the mission of conserving and restoring the natural and cultural resources of the Chesapeake Bay watershed, and using new technologies to do so. Leslie Canavera, the founder and CEO of PolArctic, a Lorton-based oceanographic and data science company with a focus on creating tailored products in the Arctic. And finally, Jennifer Sleeman, the senior AI researcher at the Johns Hopkins University Applied Physics Laboratory, where her latest work featured the use of deep learning technology for climate tipping point discovery. Awesome. So let's go ahead and get into it. To start us off, I'm just gonna throw a softball at you guys here. What are some of the most pressing climate issues affecting us over the next 10 years, and what role could AI-driven solutions play in addressing them? And you can go ahead and feel free to popcorn that around. Leslie, if you want to go ahead and start there.
Sure. So I'm a Yupik, Alaska native. I'm from Alaska, and one of the reasons we're focused on the Arctic is because I'm from there, and so that's home. I've seen firsthand some of the changes over my life for how the Arctic has changed, how some of the diversity, biodiversity, the habitat, the sea ice, and all of that's changing. And there's been a lot of studies that have been going on with saying that parts of the Arctic are warming 4 times faster than other parts of the globe. And you can see that with a lot of the sea ice, those habitats, how that's impacting the cold pool in the Bering Sea, the when and where the ice is going to form, and that's impacting a lot of our communities. And a lot of Alaskan communities don't have roads to get to them. You have to either fly to them on like a 2-seater Cessna, or to use a boat with a barge. So there's these hub communities, then they go to these smaller little communities. But to be able to get to those big hub communities, they're a mile long and 1/4 mile wide, those are the big ones, you need a barge, and these shallow draft barges need to know when they can go in to be able to get those supplies. And even with a lot of the sockeye salmon in the Kuskokwim, you see fisheries collapses that are happening. That's a subsistence food that our communities really rely on. And being able to get those to be able to survive for cultural reasons, for just being able to have food to put on their table, there's a lot of things that are impacting that. So knowing when and where that ice is going to be is really important, so you can get supplies into those villages. But also a big challenge with those shallow draft barges is being able to find zero. And that's where the ocean is meeting that land, because as the permafrost is eroding and melting, it's just eroding into the ocean. And so many of those places in Alaska, the last time they were mapped was about 100 years ago by leadline. And we can use artificial intelligence to map them quickly and fast. So like after the typhoon that happened in Alaska, we could remap the shoreline within days, so the shallow draft barges could understand like where that is, so they don't have to bump and feel their way in. And then they also could know, by us using artificial intelligence to forecast that seasonal ice, they were able to understand when that ice season was and when the last barge could get in safely to be able to deliver things. So I think as we experience a lot more climate change and variability, artificial intelligence provides a really good basis to be able to model that in a ways that really help the communities adapt to that new kind of era.
Yeah, absolutely. Thanks for providing all that background as well. Kumar.
So I work in conservation and biodiversity, and then to some extent biogeography. So my examples are related to biodiversity and conservation, because this is an existential crisis that we are experiencing right now. Biodiversity loss is a real problem, a massive one. And when we lose a species, either locally or globally, it has an impact on the system. And that impact is cumulative if you think about like what happens over time, right? So AI can be useful in detecting where that's going to happen and how we can solve it. Mm-hmm. So it's biodiversity.
Awesome, thank you. And Jennifer, what do you say are some of the most pressing climate issues affecting us over the next 10 years or so? And what's the role that AI could provide in solving some of those issues?
Sure. I think the main concern is kind of reaching those temperature thresholds in the next 10 years, and that has a huge effect, and we're already starting to see some of the effects from that. And it's great to hear your description of what's going on at the local level. So what we do is we're studying this concept of climate tipping points, and the really what we're looking at is across these climate systems you have this interconnected graph. And so when you reach some kind of threshold in one of these systems, there's a chance you could have this kind of cascade effect where others are also going to reach a threshold. And we don't understand that well enough yet. And we don't understand what are some of the mitigation or intervention steps we can take to try to avoid them. And what I see at this point as a really important part of this is we know we're going to reach these thresholds. Even if we were to reduce emissions, we're still going to get there. We do need to reduce emissions, but we're still going to reach those thresholds. And the effects of, say, sea surface temperature increasing, there's a lot of effects that are really subtle that make huge impacts. So, for example, we study the Atlantic meridional overturning circulation. We've seen a slowing of the AMOC, and we've seen the effects of that. We've seen colder than normal temperatures in Europe. We see sea level rise occur, more drastic hurricanes. So if we get actually a full collapse of the AMOC, the effects of that could be concerning. And when you think about that, take, for example, another system like coral reefs. Coral reefs, they provide for coastal regions. They're very important for basically providing a structure that breaks your waves down. And so if you couple something like sea level rise with a degradation in coral reefs, so you have larger than normal waves, the effect of that is flooding in these coastal regions, loss of property, food insecurities, because you also have now ecological changes that are occurring. So I think the important thing that I'm conveying today is that understanding these systems well and when they're going to tip is going to give us the information we need to actually adapt. And I think that's an important aspect of this conversation.
Amazing, thank you. So, now that you guys have kind of discussed some of the main uses that you've seen of AI, and it's interesting, Jennifer, having you go last, because it actually sounds like the tipping points affect both the biodiversity and the sea ice, as we talked about there. So how has AI, some of your AI projects, helped to transform previously time or labor intensive processes? And have they revealed any insights that were previously impossible to gain with traditional methods? So Leslie, you started to speak to this of you can do it quicker and faster. So can you dive a little bit more into that?
Sure, yeah. So currently the group that does sea ice forecasting for the United States is NOAA. And there are 3 analysts who do it by hand in an office in Alaska. And what they do is they take imagery and they overlay a couple different models, and then they draw where the ice will be in a few days. And that's the current system for our forecasts. And so our artificial intelligence is able to do that much faster, pretty much instantaneously, to be able to do it in much more accuracy as well. So NOAA's, our 10-day forecast using artificial intelligence is more accurate than NOAA's 5-day forecast, for example. And it's a lot more detailed, and we're able to do it every day, as opposed to they can only do it 3 times a week.
So we recently developed a wetland predictive model, and I have my team that work on this project, including my important collaborator, Michael Evans. And this wetland predictive model, what it does is it grabs the satellite imageries, and then it predicts wetland at 1 meter by 1 meter resolution, which means it's very fine detailed. Now, why is this important? We have this the inventory of wetland called National Wetland Inventory, NWI, and that has been created for the whole country over a period of like many decades. But the challenge with wetland is it's not just one kind of feature. It's like some wetlands have water on the surface, some wetlands have water beneath the surface. The vegetation mixture is very different, and some wetlands are permanent, some are ephemeral, some are just seasonal, and some wetlands just like disappear, and some actually form, and they actually shift the boundary over time, seasonally. So challenge is, because it's a moving target, we have to have a strategy to delineate the boundary of the wetland. And wetlands are called nature's supermarkets, kidneys of the landscape, because they have so many ecosystem services, including they act as buffer for flood and drought. They provide, they are very important carbon sinks. They are very rich in biodiversity. Many ecosystem services they provide. So now protecting wetlands is important, and unfortunately we have lost 1/3 of the wetlands since 1900 in North America. The world has lost 2/3, and some wetlands are very small and they don't even exist in the regional inventory. And now, how do we map the wetland on a routine basis so that we have an updated map of this moving target? And National Wetland Inventory does not get updated very frequently. Sometimes they go back to the same wetland after like decades. We just don't have resources, and there are so many wetlands. All right, so for that reason, we developed this AI system. And this AI system grabs the satellite images, 28 of them, from different seasons, and we train an AI model, and that delineates the boundary of the wetland every season, whenever you want. So this season I want the map of the wetlands. I grab the imageries this season and then get the predictions. Next season I get another predictions, and the wetlands that have shifted over time will actually get reflected there. And interestingly, this National Wetland Inventory has been criticized for being inaccurate and outdated for good reasons. Now, our AI has detected the problematic data set in inventory. That's the data that we use for training AI model, but apparently the AI model has actually detected problems in the training data itself. So those wetlands that existed before and now we have parking lots, our AI says, oh, there is not a wetland here. And there are new wetlands that formed over time, and our wetland says, although it does not exist in the reference truth, which is the inventory data, but our model says there are wetlands. So how this actually made a difference? Until now, the wetland mapping has relied on traditional machine learning, and that takes a lot of manual curation of data, and those models are good only if you apply that in a small area, let's say. And you have to have domain expertise to create some features, so manual feature engineering. With that, those models work fine. But our goal is to develop an AI system so that it is useful without any manual curation of data or creation of features. And just grabbing the raw data from satellite, our model is working fine.
Awesome.
So it's fast, it's accurate. It does not need any manual input of like data curation or feature engineering.
And as you've been running that model, I know, how long has it been up?
We have trained the model for 4 different locations. And one aspect of the challenge of AI is generalization or generalizability. So the model needs to be retrained to many more areas so that it becomes useful for much larger geography. But as a proof of concept, it works very well in those areas where it has been trained on.
And what's like, if you had to give the accuracy, like a percentage?
It's a 94%.
Okay.
And another thing that is wetland predictive models routinely use LiDAR because LiDAR have very characteristics return in inundated areas. So it's a must, let's say. But we showed that, and LiDAR, even though it is free, it's really heavy. You need like many tera or petabytes of data if you want to use LiDAR for model predictions. So we wanted to see if we really need LiDAR, and what we saw was without LiDAR, our accuracy is 92%. With LiDAR, and there is something called geomorphon that's derived from digital elevation model. If we add those 2 variables, then we improve the accuracy just by 2%. Meaning, without those variables, it is still very decent, very high accuracy.
Awesome. Thank you for that. And Jennifer, to you, how have you seen some of your AI projects help to transform either time-intensive or labor-intensive projects?
Yeah, so so climate tipping points is grounded by bifurcation theory. And so the idea here is that you reach some point and then it causes an abrupt shift or abrupt change in state. And so currently using the high performance computing environment for climate modeling, you actually cannot model these kinds of problems. It's intractable. So this is why AI is incredibly important, because what we're hoping to do is reduce it's just a very high dimensionality. There's a lot of parameters, a lot of differential equations involved in studying these problems. So if we can reduce the dimensionality, but still accurately represent the dynamics, then we can study these problems. And that's what we've done with our AI methodology. And we're pushing towards this area of AI scientific discovery with the models that we've built. So we used a generative adversarial network, and it's a very novel kind of network. So generative adversarial networks play this adversarial game. It involves 2 neural networks that are in this kind of game where one is actually trying to generate new things. So in case of images, new images. In the case of our work, new models. And these generators are trying to create models that are going to cause tipping points. And on the discriminator side, the other network, it's trying to learn how to discern is this model a tipping point model, or is it a model that won't tip? And when it's training, it's using a surrogate model. That's a reduced model. So take one of these very large climate models. You're reducing the number of parameters. That's a reduced model. It still accurately represents the dynamics, but allows you to study the problem. We do that for the oceans. And so we run, as it's training in model time, we run actually the models out to get the answer. We govern all of this with something called a neurosymbolic language. So what we're trying to do is provide a way to give the scientists explainability and interpretability of what the AI is doing. Because in this space, scientists tend not to trust deep learning because they're black boxes. You don't quite know how it gets to the conclusions. So what you try to do with this model is provide a way for your scientists to interrogate the models. So with the neurosymbolic language, what we do is we provide this bidirectional translation between natural language questions and symbolic programs that our AI methods use. And when the AI methods are training, they can actually generate the symbolic programs that get translated into natural language questions. And those two models work together. And what that has given us the ability to do is to show that if we randomly generate 2,000 questions about the AMOC, and we actually run an experiment where the neurosymbolic translates those questions into neurosymbolic representations. The GAN's trained, so now the GAN is just trying to answer those questions. And the questions are typically like, if I introduce this amount of fresh water into the north, will the AMOC collapse? Or if, because the AMOC is all about, this is called the conveyor belt of the oceans, very sensitive to salinity changes, temperature changes, so fresh water could have a real effect. So I can ask these questions, and then I can use the trained GAN to answer them, and without running the models at all. It's already trained. You get a tremendous speed up, and we do a very good job actually at in terms of accuracy. We get right now with kind of these simpler questions, we get close to 100% accuracy in F-measure scores for them, for both the translation and the predictions. Now, those are questions that are mapped very closely to the vectors that we use for these models, where our team is currently working on more complex questions, more scientific questions that are very hard to decompose. So this is where we're using large language models. As you might know, ChatGPT is one of these large language models. So you can train them on your own scientific literature and teach them all about your domain. So then they actually are well versed on understanding how to answer, how to decompose these questions. So that's where our work is headed, and that's why I call it, we're on this path to scientific discovery using AI. And I think it's a very exciting space right now.
Awesome.
Yeah.
So now that we've talked about some of the applications and some of the use cases that you guys have seen in your different domains, what are some of the obstacles and limitations of using AI in either ecology or climate work as you've seen so far? Feel free.
So one of the big challenges that we've had is getting people to understand what artificial intelligence is. And so that's been absolutely one of the biggest things for us. As soon as we say artificial intelligence, people are like, the Terminator. You're like, nope. So that's been a real thing for us, is trying to communicate in a variety of different ways what it is, the benefits that it brings, and in kind of situations like this where we're able to explain it a lot more, and instead of just like hand waving and saying artificial intelligence, especially because there are so many different types of models in artificial intelligence. Then it gets nuanced when you're talking about them, and so the culture shift in getting people to understand what artificial intelligence is, I think, is one of the biggest things for us, for an adaptation and understanding for the Arctic communities.
Yeah, absolutely.
I totally agree, because every time I go to scientific conferences, I go to non-academic settings, everybody's excited about AI, okay? The business, the industries. but in academic settings, there is a very slow adoption of AI technologies, and it's partly because it's not because they can't understand it. It's I think something else that I don't understand. But I think the phrase called black box algorithm has some negative connotation. To me, it is what it means is it's a very complex model that we cannot interpret easily. It doesn't mean it does not work and it does not have the predictive power. It does have predictive power. That's why we use it for predictions. And there are simpler models, let's say linear models under linear model framework. They don't perform very well in terms of predictions, but they do very well when you want to understand a system. So this we need some shift in the mindset, and I think that's happening at some speed now. And I think another challenge is the other kind of like traditional machine learning. So by the way, when we talk about AI, most of the times we refer to deep learning technologies, okay? But AI is anything, all kinds of algorithm that helps us predict something. That's called AI. But specifically speaking about deep learning, this algorithm needs a huge amount of data. Only then it's able to understand and learn the patterns, the deeply hidden patterns, and after learning that, it can be very powerful in giving predictions. So data availability and data quality is another issue.
Yeah. And Jennifer, for you, what have you seen as some of the limitations?
Yeah, I mean, I think I agree with both points, but in addition to that, I think when you're trying to solve these problems in these scientific domains, you have to form multidisciplinary teams. Yeah. And there's a lot of challenge to that because I'm an AI researcher, and I didn't know anything about the AMOC when I started this project, but I had to learn about it if I'm going to build deep learning models. So there's, there's a lot of upfront interchange. There's a language barrier. We're talking in different lexicons, so we've got to overcome that. And you have to build these teams that can work together, and it takes time to do that. I mean, it usually takes about 6 months for AI researchers to just kind of get up to speed in the space and start to be able to make a contribution. So. And the other thing I'll add to that is the validation of the machine learning methods. I mean, in some cases, we also do work for NASA and NOAA in the area of air quality and wildfires. And so in this case, we can do validation by comparing to the model output. But in the case that I described with tipping points, you have to try to run in the high performance computing environment, something that you started out not being able to do to begin with. So now you have to figure out, okay, what is a valid way to evaluate these methods? And then once we turn them loose, which we've done, and they're making their own discoveries, how to ensure that those discoveries truly are, in fact, discoveries. And so yeah, there are those additional challenges, I think, too.
Yeah, absolutely. And that's a great point to bring up as well, the different perspectives that you have to bring to solve problems.
Yeah.
Leslie, I want to turn specifically to you, and I'd like to ask, you started to bring this up, and I'd like to come back to it. Why is it important to both understand and incorporate indigenous knowledge into the AI models that you specifically work with? And how can businesses and researchers ensure that they're including these perspectives respectfully without co-opting or replacing them?
Yeah. So I think it comes back to those multidisciplinary teams and being able to have this wider perspective. And artificial intelligence uses a lot of data. The challenge with that is, first, the Arctic is a data desert, and there isn't a lot of data collected in the Arctic because it's difficult to get that. With that said, there is not a lot of traditional Western science collected in the Arctic. There are people who have lived there for thousands of years who have just this deep intrinsic knowledge of where they live, how it interacts with them, the animals that live there. And so we did a project in Hudson Bay, Canada, and it's for the Belcher Islands, the community of Sanikiluaq. and they had a challenge because there had been some dams that had been built recently. It changed some circulation patterns in there, and so they had some subsistence and some just food security issues, and they wanted to look for new areas that they could identify for both a marine protected area, but then potentially also in concert a commercial inshore fishery. But there wasn't enough data to be able to do that kind of study. So we were able to work with satellite data, with the university that had done some trawl samples, but then also the local community, and get information from them and talk from their elders in the group, and they said here's a map. Where do you find sea scallops? And they said, here we find them, here we find them, here we find them. So they were able to say, here's where we find these different things. We were able to take those maps, rasterize them, which means we gave each pixel a value, train a neural network on both the satellite imagery, the trawl data, and their actual indigenous knowledge for the local area. We're able to extrapolate to new areas and find new areas they should go check. They had a research vessel that belonged to their community. They went and looked at those areas, and it was validated the model's results. And it was the first time that we've seen a neural network trained on indigenous knowledge, but then also blended with these others that made it stronger and more adaptable for that community. And so they were able to then take that and build those, what they actually wanted. So one of the reasons we're a business and not a nonprofit is because we can protect that data better, and instead of being like an academic researcher as well. And there's a lot of challenges with that because you have to publish a lot of your research. We don't have to do that. We can protect all of their data ethically by doing those projects for them, and it's their data. They get to keep it. We don't sell it. We don't resell it. It's theirs. And so that's one of the other big things that's important, is being able to build that trust and to have that data available for the future, and it's theirs, and they get to decide how and what that is in the future.
Absolutely. Thank you for providing that example. Kumar, I'd like to turn to you and ask, what is species distribution modeling? And could you elaborate more on how it can help us understand the relationship between biodiversity, climate resilience, and human health?
All right. So let me change the order, okay? I'll talk
Sure.
about the broader topics, and then I'll come to species distribution modeling. So climate change, biodiversity, and human health.
Mm-hmm.
All right. So all of these are existential crises, right? The climate change is happening. It's real. We used to call it global warming back in time, and then we realized, oh, it's not just warming, the variability and everything is changing. So climate change, and it's not just climate, it's environmental change. In fact, many variables that don't fall under the domain of climate are also changing. So everything is changing. So when things like this happen, it has a massive impact. The biomes are changing, species are shifting towards the pole and towards the higher elevation. And this is not a hypothesis. It's a dominant pattern that has been observed in thousands and thousands of species across the world. What happens when species shift? When I was in grad school, early days of grad school, I made a prediction about dengue. Okay, it's a disease transmitted by mosquito, and I came from Nepal, and so I was interested in understanding the dynamics of the disease in that area. So Nepal almost never had any incidences of dengue, except a few incidences in short and very lowland locations of lowland areas of Nepal. And my model, it was machine learning. It predicted that we'll see many incidences of dengue with very high probability in Nepal. And guess what? It has been a few years. We have so many cases of dengue in Nepal now. And that's happening because the temperature is shifting, and the species are tracking the temperature. They either have to move or they have to adapt enough to be able to live there, right? And both things are happening, but the climate change is so fast. What happens more often than not is species go extinct at the trailing edge, and then they keep moving to new areas. When that happens, the species don't exist in isolation. They exist in a network, ecological network, and there are so many exchanges. And then the exchange about food is called food web. And these multi-directional complex network of exchanges and dependency get like disrupted when species move, because they don't move together. Some species track the climate, some cannot. Some don't have the enough the right type of habitat ready there, and so that's happening. So health impact of the shifting of the biodiversity and the species is real. That's happening, and the loss of ecosystem services because the ecological network is being disrupted. That's happening, and along with that is something called habitat destruction. That is another factor that has contributed a lot to the biodiversity, and it's another negative factor. One thing I would like to actually mention about habitat destruction is, as we are changing the landscape, we are making small fragments of natural landscapes, right? And this is something that's very relevant to the Vista Green as well. We live in urban space, so we have the nature there, maybe a few blocks away from your home, but the natural landscape has been fragmented. When you fragment a natural landscape, let's forget about climate change, let's forget about habitat destruction, okay? You have the native, very ideal condition. Just fragment that by creating tall walls or maybe putting tall nets, and species cannot pass through the nets or a wall, then many species will go extinct over time. That's because species survive, the populations survive with a process called metapopulation dynamics. What happens is some individual living in this area, the population living in this area, can go extinct by chance. That's called drift this year. And then the populations living somewhere in Virginia can come here, and then they continue the population here. And 2 years later, that population can go extinct, and individuals that are here will immigrate to that location and continue the population, and that maintains the population throughout the species range. But if we fragment, then all of these fragmented populations have very high, much higher, 10 times higher, 20 times higher chances of going extinct just by stochastic processes. So fragmentation is a big enemy of conservation. If we connect the landscape, the natural landscape, to our man-managed landscape, our lot area, by planting natural plants, that helps tremendously. So coming back to now climate change, now let's add fragmentation and climate change and all sorts of problems. It's a real problem. All right, now coming back to species distribution modeling, that's what I do. That's one of my projects, ongoing projects. This is a framework that maps the distribution of species. Let's talk about the horioids, these beautiful butterflies, less than 5 centimeter wing length. These guys live in open woodland, mostly. They prefer to live in sandy soil habitat. The larvae feed on legumes and the plants of Fabaceae families. The adults take nectar from many species. So that means where they can live actually directly depends on where those plants actually grow and survive, right? And after winter, only when certain amount of heat is accumulated, and we call it growing degradation, when GDT of about 286 is accumulated, then the species can disperse. And there are so many things that actually determine when it is active, where it can survive, and where it cannot survive. And that is collectively called conditions and resources. This domain of conditions and resources applies to every single species in the world, except non-natural species like us. We can survive anywhere. And look at this building where we live in. It's a microclimate we create here, right? we have AC, we have all sorts of environment that we need to survive right here. So for natural species, these environmental conditions and resources decide or determine where they can exist. But we cannot use a simple kind of numerical approach to determine where they can exist. If you really want to predict where they exist, we need to use some sophisticated algorithms and models, machine learning and AI. And I use these technologies to predict where a species exists. In other words, what I do is I grab the species occurrences, which is the longitude and latitude of many locations of a given species, let's say the Horias, and I have, let's say, 400 locations from where that species has been reported in different time points, okay, by many people. And these are public repositories. And I do some sort of data cleaning, and then I run my models, and that model tells me everywhere in the 48 states, or maybe North America, wherever I want to predict the distribution, where are every grid cells, pixels, with certain probability of finding these species. And that way, I can see it. It's like a heat map of, let's say, weather predictions. When you look at weather predictions, you see the entire America has like different color. The same way, we can see different color for the prediction of its species distribution. And based on that, we can see where are the highly suitable habitats, core habitats, marginally suitable habitats, and other kind of habitats, and where we can draw some sort of species range, and that serves as a baseline data for conservation. Now, when you have this data available for many species of concern, threatened species, endangered species, that's what I am working on right now, and that data can be stacked together, and you can look into the data and see where are the areas that support very high number of threatened or endangered species. And now, I also make the predictions of future, and here is the current distribution of a species, and that's the future distribution of the species. Now, I need to find the corridor, because the species has to move to that future location in stepping stones, and we need to protect those stepping stones too, or corridors. And where are the most likely corridor that many species are likely to use over time. So machine learning and AI has it's powerful enough to model those kind of problems or solve those kind of problems.
Awesome. Thank you for that. Jennifer, I'd like to go back to you. You kind of gave us examples of some of these climate tipping points and the way that they can affect entire systems. Can you share some examples of those specific climate tipping points we are approaching, or perhaps some that have already passed?
Sure, and they are at different scales. There's actually literature out there with regards to estimating how likely we are to reach tipping points, and so coral reef is something that we're closely approaching, which is why we're trying to study that. There was a new research paper that was just published, I think last month, regarding the AMOC. So I think most people didn't assume that AMOC would collapse in our lifetime, and it looks like there have been some studies done where it could happen in the next 25 years. We're approaching some tipping points with regards to permafrost is very imminent. The Arctic melting is also, and also the boreal forest and wildfires. So those are many of the ones that we're tracking because they seem like they could happen in our lifetime, and they're of importance, and we can see them. We can see the effects of them at this point. So, as I mentioned, the real concern here is when one tips, and it has an influence on the others. Now, all of those projections that were made, they changed now, right? Because it's hard to account for the fact that you're going to have influence from one of these others tipping. So, and that's, I think, where there's some concern, because then you get maybe projections that are happening faster than you had anticipated. And so, again, that's why an important component of our study is studying adaptation or mitigation, steps to take to either avoid it, or if you do encounter a tipping point where, meaning you enter into this new state, how are you going to adapt as a society? And I think those are important questions to begin answering now versus later.
Absolutely.
Yeah.
Thank you for that. Thank you for providing those concrete examples. So at this point, I'd like to go ahead and turn to you guys in the audience. You guys can kind of see where these three speakers come from, their different perspectives and their different expertises that they have, and the ways that they've used AI in their research and into their business as well. So if anybody came with any burning questions, now would be your chance. Now would be your opportunity to ask those. Sam, go ahead.
Thanks. So first of all, thanks for hosting this Instagram. Thanks to the panelists for coming. For Kumar, I did question, so I did pull up your paper actually because I saw you linked to it in the description. I was reading through that a little bit.
Which one are you talking about?
I think it was your 2020 paper. Science of the Total Environment.
Oh yeah, that's the wetland AI.
Yeah.
Yeah.
So I guess when you said 1 meter satellite data, my ears kind of perked up, and that's why I pulled up your paper. So can you talk a little bit more about what data sources you use?
It's NAPE.
It's named, okay.
It's a very good question, by the way. It's NAPE data set that comes in 4 bands, RGB and the NVDA. That's 1 by 1 meter resolution, but it used to come every 4 or 5 years.
Yeah.
So it's very high quality data.
Yeah.
They curate the data before they make it available. Very high resolution, very high quality, but very low temporal resolution. You have to wait for many years, and just 4 bands.
Yeah.
Now, my team coupled that data with Sentinel, and we grabbed, I think, 7 or 8 bands of Sentinel. And Sentinel comes in, the data we used was 20 meter resolution data. And Sentinel data is like, you have the data every few days, I think. So it means you have like, in a season, you have like a stack of many layers of data, which also means we can use the data for every season separately, because the land cover does look very different in different seasons. And by combining high quality, high resolution, but pure band, and let's say a little lesser quality, but very high frequency, temporal resolution, and multiple bands, we have this set of data set that probably represented many aspects of land cover, and that's how we trained the model.
Cool. So I've actually done a lot of work in this space, so I'll find you after to ask some follow-ups.
Absolutely, I'd love to. Yeah.
One other thing I wanted to ask just for the room is, have you considered, you mentioned LiDAR as one of the sets or data sets you used. Did you consider using Sentinel-1 data, SAR data?
Yes. 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 In the model retraining stage, that's actually one of my items to discuss with my team. Yes, we are actually thinking about that as well.
Cool. Thanks.
Yes.
Awesome. Other questions?
Oh, hi. Yes, thank you, Emily and Dave Bethesda Green, and for facilitating this, and for the 3 of you carving out time today. Really appreciate it. I work for Montgomery County's local government in the Department of Environmental Protection, so I'm particularly interested in an application of AI as it relates to local issues. I mean, should we be hiring an AI climate specialist? Should we be submitting that in our budget for the next fiscal year? I mean, and what do you envision? Like, can we say, okay, well, we predict this many high heat days, and that's going to translate into this many, deaths at a hospital, or the respiratory problems, or What about even gauging people's behavioral patterns? Well, if we want to do a campaign to engage everyone on climate action to do their part, what are the messages that resonate? What are the pathways that are most easy with the highest impact? Is it possible to use it for those sorts of things? Yeah, I'd love your thoughts.
Yeah, so I do a lot of work with air quality. I work with NOAA and NASA on this problem, and I think, yes, you know, what I'm amazed at is the number of people that do not realize that we have a poor air quality day. And I think it's important because if you fall into any of these sensitivity groups, you should not be outside without a mask, particularly when we have wildfires that are causing PM 2.5 levels to be in that elevated state. So, and you can make these kind of predictions using machine learning, more generally AI methods, and you can do it based on a number of factors. You know, the geographical location, the number of people in the environment, you know, is it rural area, is it a city? There are a lot of factors that go into some of these predictions, and machine learning works very well for these kinds of problems. And I think, I mean, I'm biased, but I suggest, yes, that you should have, begin thinking about having AI specialists as part of the team. Because I think it solves two things. One, you can answer questions faster, and two, you tend to get better accuracy if you have the right data available. And data is always the key with machine learning problems. That it's an important factor in this. But yeah, I mean, and things are changing. The landscape is changing very quickly. I'll tell you that. In 2017, there was a lot of reluctance in some of these spaces using deep learning and machine learning in general, but now it's very different. I mean, we can show. NVIDIA's produced a model called ForecastNet that does weather prediction very well, and we're using models such as that to do prediction of things like pollution. So, yeah.
So a quick addition to what Jennifer said. So if you are investing your dollar of this Montgomery County in solving problems, there are so many problems, right? And there are some problems that affect not just Montgomery County, but let's say the whole country. And it's probably a good effort to collaborate with others in solving those problems. For example, pollution. The pollutants don't come from the border of Montgomery County. It comes from sources that are very far from us, right? So collaborating with others probably is a good idea because you also need big data, and also when you invest your dollar, the data source is an very important consideration, because if you have to use a lot of your money in just accessing data, probably that's not a good choice.
Yeah, just to add to that, because it's a very important point. I mean, the resources that you need for doing these kinds of projects. I mean, we often need multiple sort of GPU systems, and when you're working particularly with data related to air quality or weather, we're talking on the order of terabytes of data. So you have to factor in those sorts of things as part of it. You know, how are you going to support that kind of effort? And they're real problems, especially as you start to increase the number of projects in that space.
Leslie, I was just going to say, as somebody who's worked with local communities, have you seen it benefit them or affect them?
I guess my biggest thing would be to really prioritize what you'd be interested in, and to make sure that you have that identified, because AI researchers, there's so many different types of models, there's so many different types of languages, and you might hire somebody who's really good at large language models, but you really need environmental modeling. So you need to be careful and make sure that you understand what you're looking for and your priorities, and to be able to communicate those, because I think there's also so many companies that are doing it, that are would be great to be able to support that. And that way you wouldn't be doing all of the like maybe the infrastructure with like buying those GPUs or high power compute, but you'd be able to get it for less of a cost for doing something like that. So it's important for like the community to understand kind of like what do you need for your community, what like could you get from the bigger resources from like maybe like a NOAA or a NASA with the products they already have available, and then what could you do to really build on that to add value to the community. So
Larry, I saw your hand back there.
Thank you all for serving and hosting. Larry Davis with Gray Mechanics. We develop cloud networks with which we can deploy varying sensors that collect data and streamline that data that can be user-friendly for clients and groups that we serve. Could you talk a little bit about when it comes to galvanizing and aggregating different data sets that are either have been stored and you can access, or if it's live data points from like live sensoring technology, are there certain hurdles that should be considered when inputting those different data points simultaneously in order to develop more accurate models?
Yes, yes. We actually had this challenge when we trained the wetland model. Some of the data set, for example, LiDAR and geomorphin, there was some derivative of LiDAR that my team created. And the team also created geomorphin. So there are some data set that are sitting in our computers, but the rest of the data set, we are grabbing that from satellite, right? And we trained the model, we trained the first model in Google Cloud Platform, Google Colab. So Google Colab, you can actually push your data through Google Drive and then combine that data set with satellite data set. Satellite data. So the best experience that we had was every time you want to use your data set from your computer, it's like it takes a huge amount of time figuring out everything and also pushing the data to the cloud. Rather than that, if the same data or similar data exists somewhere in the cloud, maybe some other companies have that in some bucket, just talk to them just for like a couple $1,000, maybe they can let you use it. That way, it's a lot better, faster, and much more efficient. And also remember, what's the goal of developing this AI system? Just to showcase it works or to democratize data. If the latter is the goal, then you have to use the data set that's freely and instantly and easily available to everybody. And that's going to be satellite, right? Rather than your personal data from your computer.
Thank you.
I might just add to that there are also challenges related to resolution. So when you do data fusion kinds of problems, you're going to be working with information that could be at different spatial and temporal resolution, and that's something that you have to work through when you start working with these different sorts of data sources.
Leslie, any tips and tricks from you there, working with different sets of data?
both of those were totally spot on. I think the biggest thing is really realizing if you're doing like more of a research project or if you're operationalizing your model. And I think that's the biggest thing for.
Yes.
I recall at one point hearing about an asthma study where people who had asthma, I think in the Bay Area, were carrying around sensors in their, or had a program in their, an algorithm in their iPhone or in their Android, so that they actually were collecting data on air quality as they went about their normal lives, and this phone automatically reported back this data. And I'm just wondering if that's a service that Google or that Apple offers, this kind of on-the-ground data collection that is publicly available for free, or if that's a fee. And also I was curious if there's an AI program that keeps track of all of this, so that when you want to put a project together to try to figure out, for your own Montgomery County or wherever, what's out there? What are the databases that are readily available? How much? What are the fees, if there are any fees available? How do you manage it all? That's what I'm trying to figure out. My God, it's just mind-boggling huge as far as trying to just wrap your head around what's even available, what has already been done, and what's already in the bucket, as you call it. How do you keep track of it all? Is there an AI program that does that?
I'm sure someone's building one. So I think a lot of these sensors that people wear, that track a lot of things.
Well,
but
yeah, just even your phone. I mean,
right. It's one of those things where it's a data collect, and it's a service to you that can monitor your sleep, monitor your air quality, monitor how much you exercise, all of those different things. These companies, they are collecting all of that data and monetizing it, and it's one of those things that terms of service that you scroll through and you're like, oh goodness, and then you hit yes, fine, because that's a big ethical question now of this data collect. So, but I do think that there are a ton of overlapping data sets and information and things like that, but I don't know of anybody who has actually got a hold on what actually exists everywhere. I don't think that exists yet, but maybe after AGI.
It just seems that's a logical step.
Absolutely, knowing what's
just,
available.
Just to try to manage what you got.
There are sensors, for example, AirNow has sensors where people volunteer to host sensors at different locations and can track things like ozone and PM 2.5 using those. But I am not aware of, so what you're describing is kind of sensors everywhere, right? And then them being kind of interconnected in some way, so you can, and that I do know of some efforts right now that are underway to try to do that, particularly for, when you think about areas where there's a lot of poverty. And you want to get an understanding of the air pollution inside the house and also outside, and then how they interplay with each other. Those are very important studies that are underway. And also, there's all kinds of things you can do with regards to how you build the structure of the home, to painting the streets, the asphalt white, that can help with reducing pollution. And so I think all of that, there's quite a few efforts, that are underway for trying to tackle these.
But also, it just seems to me that if a lot of this research is being done with public money, then the results should all be in public domain, and it should be able to be reused over and over. I mean, free of charge. I mean, it seems to me. But then you hear about Elon Musk and his power, and you just shudder. You just shudder. And for anyone who isn't aware of what I just referred to, I referenced the New Yorker article that was published 3 days ago on Elon Musk. Must read. So.
Roman Farrow.
Can I ask a question just in terms of each of you have described amazing projects that have a huge sort of public good interest, and I'm just wondering, in your own spheres of work, do you find that AI is used for, say, private gain that might be at variance to your efforts? So, for instance, the example of the fertile sea scallop area, if another company found through AI that was a great place to get magnesium modules, or a developer using AI to say, well, this really wetland isn't really wetland, or in climate change that this might actually, the collapse of this current may actually improve fishing stocks in for this country. Do you see sort of a competing use of AI in some of the areas that you're working in?
Yeah, absolutely. So again, the Arctic in Alaska, oil exploration is still happening, and
is that AI generated at this point? Yeah.
They use a lot of technology, and they're using artificial intelligence for being able to identify some of these things. So I do see some competing, being able to identify when the ice is gone, and then you can now put an offshore oil platform there. There's things that other competing interests would want to know. So.
So in my case, so my colleague Michael Evans, he has a pretty cool AI system that detects solar arrays, again using satellite data, and that's how he started the project. So that algorithm works really well. Then we thought about, he thought about what else we can do with this algorithm. Now these solar companies, they have a lot of money. They exactly know, or let's say they approximately know, what are the best locations to put solar arrays, right? Let's say for them, the revenue generated by installing the solar arrays is what matters. For us, what's the environmental impact of the solar arrays? Obviously we need it, that's a renewable energy. Yeah. But can we put those arrays in locations that are, let's say, that have least ecosystem services? Let's say that does not support many other types of, let's say, plants, or that's not a good habitat. So what he did was, rather than detecting solar arrays after they are installed, let's be forward looking and predict where the solar arrays are coming next year. So he developed that model, and that model actually predicts where are the locations that are highly likely to see solar arrays next year, in 2 years, 3 years, 4 years, and 5 years. Now we can be proactive, and we can start actually working with other agencies, companies, to protect the most important areas.
Yeah, I feel like artificial intelligence is a tool. It
Yeah.
can be used for good or bad. Like
Exactly. And certainly, companies can use that to their advantage. Yeah, I mean, in my work, because I'm mostly in the academic world, we're mostly just trying to solve some of these problems or overcome the limitations. But I can say that, you know, there's tipping points that you could see as bad, but there's also tipping points that you could see as good. And so you can use them in ways to, you know, you can study the financial system, right? And I mean, the coin tipping point, it doesn't just apply to climate. So these methods that we develop, I mean, you could apply them to different types of domains.
Awesome. We probably have time for one more question. Larry? Go ahead.
Okay. Tipping points was one of the questions that were posed in some of the model projections. Has any of your colleagues or in the research have been looking at, I know this topic doesn't really, I guess, contribute as much as it relates to climate change, but as far as for inputting data, like as far as for the changing the magnetic field, especially with the poles switching, or rapid increase of magnetic sphere changing in its speed, is that data being input into the models as well for any of the inventory or delineations or anything like that?
Not in the models that we're using currently.
Okay.
Yeah.
Awesome. That was a short question.
Yeah.
So we have time for one more. Dave.
So first of all, thank you very much for your thoughtful insights. This has been an exceptional program today. Bethesda Green is part incubator, part accelerator. We've actually been around for 15 years. We work with small businesses that are having an impact on the environment and across a whole range of different technologies. Are there some trends that you see of companies that are doing innovative things in AI that we should be looking at, that we can help scale up or support, that will have a long-term impact on environmental issues? Are there any local companies that we might want to work with as well as part of that? We have an accelerator that we work with those companies very closely and help them get capital, a whole range of support services. So, you know, we're intrigued by artificial intelligence. I think it's something that we want to track. You know, as Doug was saying, you know, we want to get our handle around it, especially where it's positive on the environmental side. And then the other question I have is, are there any other trends that you see in AI going forward that are positive, that will give us really good hope, that you see that will really have a long-term impact that could really change the game around the environment?
So I guess we are one of those organizations that are working on these, like using cutting edge technology in environment and climate change and biodiversity related problems. We work locally. So most of our focus is on Chesapeake Bay. Well, I talked about 3 AI products that we developed. Actually, we work on a few more projects, AI related projects. And I also briefly talked about the landscape, modification of landscape, fragmentation, and how we can minimize the impact of that with plantation of native plants. And there are so many ideas that we can work on, right? So yes, and we also have a lot of high resolution products that we give, like everything that we generate is freely available. So those products can also be useful. The second question, yes, as all of us indicated, AI has been a game changer in our ability to predict accurately. So the keyword here is precision, right? Very high precision prediction. So previously we used to predict what happens as an average outcome of a group. Now we are talking about, let's say, an individual outcome. So that's called precision prediction, right? Precision agriculture. For example, I think that's a good example. The how we apply pest, how we apply water to a plant, just by looking at the plant, we can predict the stress, the level of stress, and then water can be applied based on the level of stress that the AI system predicts. So those are some examples of like what's the best way of utilizing our resources and what's the best way of minimizing environmental impact. So everywhere, wherever we use it, if we use it wisely, it gives very amazing products.
Yeah, I think for your first question for being able to find businesses, I think it's going to where like there's a lot of like young people with crazy fun ideas, and being able to try to do the National Science Foundation calls it convergence, where you're able to take multiple different disciplines and bring them together and come up with these ideas. And I think that's really where you get like these catalysts for really cool ideas, and being able to like have somebody with the programming skills to be able to create like the models, but then have like other disciplines to be able to fill in those gaps that like you need an oceanographer to know about the AMOC, and like all these different kind of ideas and bringing them together. The National Science Foundation has actually the U.S. government just has a really cool program, the Small Business Innovative Research, the SBIR's programs, and that's a lot of small businesses who are trying to de-risk their technology to be able to do this. They have a group that's just focused on AI for like National Science Foundation. There's some other ones that have their programs too. So if you're interested in like looking at just like how do we look at some of those AI technologies and bring them into the area, that would be a great place to look for that, I think.
So we talked about cool things about AI, some challenges about how to create a good AI. But I think one aspect of the AI that we probably talk much today is that it come with some problems, and it's not free of problems. It can be very biased. If we rely on AI and if we train AI model with bad data, let's say biased data, the AI system can be very biased. It can give very horrible outcomes. So that's one potential problem of AI. So we talk about AI can be very biased, right? And that's a very valid concern. So that actually affects AI.
Yeah, and also just to address your questions in terms of trends, and I alluded to it earlier about this whole idea of scientific discovery, and so there's 2 key aspects there. One is the advent of large language models, and I mean, it really is. There was a time when deep learning models were applied to imaging and doing things like object recognition, and we called that the ImageNet moment, when we beat basically human level performance. And so we see that now with these large language models for language. But they do more than just use them for language. I mean, you can do code generation. There's just a lot there. So you couple that with something else, which we call foundation models. And this is very important in the scientific community right now, because when we build AI models for different types of modeling systems, we kind of build it custom to each one of those. But now we're starting to ask the question, can we build something foundational for scientific models? And then can we apply them and just kind of fine tune them to each one of these different models, so that you're building on this large model that's been trained on a vast amount of information. It learns the physics, it learns the dynamics, and now you're just applying to these different domains. That's going to allow us to make faster discovery, ask more questions that we could not ask before. And so there's a lot of promise there. And I will also, in terms of the National Science Academy, we've had some discussions and meetings around transdisciplinary teams. And so now we're trying to bring teams together from the social sciences and from the environmental sciences and from AI, and we're trying to bring all of these together to solve these really big problems. And so I think that's where the trend seems to be headed at this point. Yeah.
Thank you. A quick follow-up question to Leslie. How do you define young?
Sorry, what?
How do you define young? You said young people. I'm just teasing.
Young, it could be young at heart. It could be.
Okay.
There's lots of different ways that you define young.
Okay, stop heckling now. Thank you guys so much for coming in today. Thank you for bringing all of your expertise. Thank you to the audience for bringing all of your wonderful questions and for being engaged.